Okay, that sounds good. So today I'm just covering the first hour of the lecture on oops, I hit the wrong button. Sorry, where's the present button? Okay, yeah, just lecture 5, the first hour of it. And it's the implicit models and some introduction to some GANs. Okay, and so the motivation of learning GANs is that just on phase generation, from 2014 to I think this is a few years old, but it has gotten so much better. All the realistic faces can be generated. Fake realistic faces can be generated now. That so GANs are very good for generating photorealistic images. Okay, and so there's the other. So let me look at the. Just play this video back. Probably you've already seen it, but I'll just play it back in case you haven't. So the idea is you can go through the latent space, and the intermediates are also kind of make sense. I mean, yeah, some of the intermediates are pretty scary looking, and so, but that's okay. And yeah, there's endless examples of these kinds of things in people have made lots and lots of these things on the you can watch on YouTube. Some are even scarier and some are better. And then he also talked about this Gan art. So the artists trained the model and then they, I guess they painted it or printed it out, I'm not sure. But it's sold for $500,000. So, there is value for Gan art. And it is quite a thing with artists. I guess I didn't know that, but there's a lot of interest in generating art with GANs. Okay, and not just photorealistic images, but all different kinds of. And as Peter said, don't have to write code or anything like that. You just set up the software and you can put different training examples, and then you can play around with the parameters, and you can have produce new art. So it's also a actually useful tool than just for researchers. Okay, so oh, there's a chat question. Okay. And so I'm not sure what the link is for, sorry. AI playground, okay. Okay, here.
Can you hear me?
Yep, it's pretty faint, but go ahead.
Yeah, it's for the stuff that you just talked about. The
okay.
Different, Gan and the interpolation of the faces. This is the NVIDIA's playground for doing all those stuff.
Oh, okay. I think big GAN, some of the latest work is in GANs come from and is from NVIDIA researchers, I think. So the later on lectures, way down the line. But yeah, okay, great. This is a good link. Yeah, this, I think we talk about it this lecture or the next lecture, all of these things. But yeah, most of these will be slightly boring. It's like more older ones from 2017. So, but just like the basics of it. Okay, but there's plenty of motivation on why to learn about GANs. Okay, so let's see what we've done so far. So we looked at autoregressive models like MADE, pixel RNN or pixel CNN, gated, all these different things, flow models, autoregressive flows, latent variable models, pixel VAE, VQVAE. So all of them had one thing in common, was that we calculated the likelihood. So we knew the exact, or we knew the likelihood of the latent variables, or so like everything was explicitly based around calculating likelihoods, but that likelihood, we never used it. It's just for training, but it doesn't, it really is not directly meaningful, right? So so I guess what if we could remove that? What if we just not have likelihood based um, likelihood based training at all? Because the likelihood is only used in the EM part of the algorithm, the expectation maximization part of the algorithm, and then the actual likelihood is, you can't say what is a, it's not interesting to say what is the probability of something, because it's kind of meaningless, right? Sorry, the probability of an image, certain parts of an image or something, it doesn't really mean anything. So okay, let's go to the next slide. If I can. So here in the generative models, we care about sampling. We evaluate the likelihood, we do the training, and then we do the representation. But if all we care about is sampling, what if we just want to just create new images in the same distribution? We don't really care about the likelihood, right? So, and that's exactly what the GANs serve. And so this is like a example where it's a really bad sampler. Okay, so this is Python code without any syntax highlighting. So I'll just go over this. So glob means get me all the files with this that are JPEG, and so the sample function just creates a random index into the files, and then reads the file and sends the image back. And so this sample is just for n samples, right? So it's just doing it for n times. So what it's saying is, well, you can make a sampler by just like picking a random sample from your image. And I know ImageNet has a million or something of the images, and you'll probably never see the same image. So you never know you're getting it from the disk or from your data. So, but this is not what we want, right? So, but this would make a perfect sampler, but because every image is realistic, but this would be kind of pointless. Okay. So what do we really want? So that goes back to the question, what we want as a sampler is, so we want to be able to smoothly interpolate across training samples. So if you take two images, I guess, and then we go into the latent space, and then we draw interpolation between all of the latent, we want a smooth interpolation and not just one image and then switch to the next one. And then make similar samples, but not the same as the training data, right? And I'll put, so we want the samples not just to be not similar to the training data, but also understand the underlying factors, like what's going on in the training distribution. So if we have images, we want the output to actually look like images that occur in the real world, and not just like a mishmash of random colors everywhere. Yeah, and then the example is suppose we train it on MNIST, then maybe we will get digits with unseen strokes, maybe like a thick pen or thinner pen, or pen that's thicker and thin on, thick on the downstroke and thin on the other stroke, on the left or the right stroke. And then with faces, maybe we have faces that are head on. Maybe there's one to the left, to the right, but then maybe you can figure out how to rotate a face so you can see it from any angle. With some latent variables, right? So that's the idea. Okay, so why implicit models? So we sample from Z, and we just whatever, we can just take any noise, and we can pass the noise through noise, meaning just some random values for Z, and pass it through a neural network, and then we'll actually get an image. And it's similar to our flow models and VAE. But so what's going to happen is that we are not going to learn we're not going to bother with the density of Z. So we won't have any of those expressions of, or we don't have to keep track of probability of Z. So in this way, it's not, you don't have to explicitly say what Z is. I mean, it is implicit because we still want to use the latent space, but it's not completely explicit here. Okay, and that's where the name implicit models comes in. But okay, so this is a okay, this is, so we get samples from this, and we have a sampler. Okay. So this is the basic idea of how implicit models work. So we have a data distribution of P data. So P data is our data distribution, and like this is the notation we'll use for the I think the rest. P data is the where the actual the real samples come from, and X is all the real samples. And Q is a sampler, so it's more like given a sampler. Sampler meaning so something that will generate our image. So Z is the latent space, right? So and phi is our parameters, and Q is our generator. And the generator is a deep neural network. And Z comes from P of Z. So you have to be a little bit careful with the notation here, because P data and PZ. So it's still the same P, but you have to have the Z mean that they're completely different distributions. But we don't want them to be the same. But right now they're like they started as being different distributions. And X created from Z using our neural network induces a density function, P model, which I haven't seen used anywhere. But yeah, this notation, but in case it does come, and I forgot that where we used it. Okay, so we do not have explicit form for our data or our model. We can only, the only thing we can do is get samples. So we can say, give me a data sample, or I can say, generate me one. But I can say, well, what is the distribution that's that underlying the generation? There's no way to access it. There's no explicit form. There's, you can ask it to generate infinite ones and calculate it, I guess, but there isn't a actual one being added to the that you have to specify, and it's being calculated by the model. And the goal, of course, is to make P model as close to P data, and then by learning this appropriate phi, which is our all the weights in our neural network, right? pretty straightforward. Okay. So we're not using the likelihood function, so we're not doing maximum likelihood at all. So what are we going to do? So what we need is to measure how far apart the actual data and the model are. So we have real data, and then we have the generated data, and we want to make sure they are in the same distribution. So with density models, we could use KL divergence. And oh, there's P model. Okay, it is being used. With density models, we can just use the KL divergence between the real and the model. And then so we have the loss function here. So objective is the loss function here. And then this is discarding all the terms independent of theta. And so we can just model as p theta of x. Right, this is what we did before in VAEs and others. So because we don't have an explicit p theta here, so we have to come up with a distance measure that's different than maximum likelihood. And so there are all these different ones. All these different distance measures that we can use. I think we will cover Jensen-Shannon divergence one, and then on this first hour. The others are later on. But this is like one type of GAN. If you use this loss function, there's this, you have different kinds, different flavors of GANs. Okay, before I go on to the original GAN, any questions? Okay, so let's go to the original GAN. This is the paper. Okay, so this is the famous Gan equation, and I think it is said in the picture. Sorry, in the artwork that was created, the signature is this actual equation. So instead of the artist signing it, they put in the Gan equation. Where do I go? Okay, so let's figure uncompress this. What's going on? So there's two neural networks. One is the generator, so that generates the image, right? So you can have some a latent vector, and then this will generate an image for you. So there's this G here, and then we have a discriminator D, which you give it an image, and it will give you the probability that it's real. So if it thinks it's, the more it thinks it's real, the higher the probability it is. So these are the two pieces here, right? So the loss function here has two parts to it. So there's the if you get the data from p data, so if it's real data, then we want to calculate the expected log of the discriminator. So this would be good if it's all one, right? So the discriminator says, yeah, this is real because it is coming from the real data. And this Z is coming from the distribution of the so the latent space. And what we want is also to calculate the discriminator of the generated, and we sort of want this to say, well, this is figure out this is fake. And so if it says it's fake, it's 0, and then so this would be log 1. And so if the discriminator is really good, then this is always one. D of x is one, and this is zero. So this is, both of them are one. But if it can't figure out, if it looks at it and I was like, I'm not sure, then it says 0.5 here, and then it gives 0.5 here, then that's a different score, right? So the game between these two is that discriminator wants to maximize this. It wants to say, well, how do I make it so that I can figure out all of these? I can make this part one by figuring out all the real ones, and make this part also one by figuring out all the real ones. But then the generator does the opposite. It says, well, I want to minimize it. I want the discriminator not to be able to distinguish this. So it will say, well, if the discriminator can't figure out if this is real or not, then it will give 0.5, or if it's unsure, or it will have incorrect answers. And I want to increase this as much as possible. So if it's fake, but it's classified as real, this number gets smaller, and so this is a smaller number, right? So and so there's a two-player game, I guess. There's a two-player game where the generator is trying to generate fake images, and the discriminator is trying to figure out what's going on, which one is real and which one is fake. And this is the loss function that we will use in the neural network. And the equilibrium is reached when the discriminator can't tell. And it's 0.5 and 0.5 for all of them. So that it can't tell between the real and the fake, and the generator is so good that it's creating it looks like it's creating samples from the same distribution as P data. So that's where we want the game to go to reach the equilibrium, right? Okay, so if you've seen GANs, this is probably a equation you've seen quite a bit. So, and pretty much this is the basic loss function that you'd put in PiTorch. Okay, so how would we do this in sort of PiTorch? So you grab some real data. Discriminator is a differentiable function, and then you say, well, the backprop. You say, well, this is a real one. So backprop, learn that this is one, and learn that this is one. So it will update its gradients. And then so you have another one where you say create some input noise, and G generator is the differentiable function also. So you create an image from G, and then you ask the discriminator, is this fake or real? And then of course it's fake. So then you have two sort of gradients going back. The discriminator loss function will say, well, it's zero. So try to adjust your gradients that way. And then the generator will say, well, you need to move your gradients so that this one gets closer to one. So there's like three sort of backwards loss dot backwards going on here. Okay. And so here's the pseudocode. So we can go into this a little bit So they say K is a hyperparameter. And so they say K is equal to 1. This is K here. Okay, so for number of training iterations for K steps, this K steps goes up to here. So let's see what they do. So you sample a mini batch of M noise samples. So you get Z1 to ZM. These are noise. And then you sample M examples from your from the image library. It's a data generating distribution, they say, but it's an image library. These are from the latent space. So then we update the discriminator using its stochastic gradient. So here we have this equation that we looked at before. So we have M examples, and then we are updating the gradients based on the real ones, and then updating the gradients based on the generated ones. And then this K just determines how many times we are updating the discriminator. Right now, the generator is fixed, and they suggest they just do it for 1. And so the next, after you update the discriminator, then the next step is to sample some noise from Z1 to ZM, and then update the generator by this gradient, just looking at this part of it. The second part of it. The first part doesn't involve the generator, right? So this can be ignored here. And so we'll only look at the second part of it. And then this is the parameters of G. Sorry, this is theta D is the parameters of the discriminator. Theta G is the parameters of the generator. So we calculate another this loss, and then we back propagate. So this is the main pseudocode. So there's there's 2 steps where there's one step where the discriminator is being updated, and you can update it as many times as you want, and then you update the generator after that. So these are 2 different steps. Here the real data and the fake data are combined together, and then it's trained in one step. Okay, and so this is the one that I was running here, the Gan lab, to see how the how it works. So this is the discriminator loss and the generator loss here, and these are the I think this is the Latin space of the generator that it's learning, and this is the discriminator. So these samples are matching up. So this is our real data, and with enough time, it matches up. And they have and then the loss start to go together. They have different samples. This is the bimodal one. This is a ring one. This is the 3 models one. And I guess you can make your own. But yeah. So it's a cool tool to play around with, and yeah, everything is in 2D. And I guess the purple is the one where it's sure that it's it's fake, and green is what it's sure it's real, because it's from our data that looks like it. Okay, can play with it's in the so this is what is this? Yeah, these are GAN sets that were generated from 2014, so from 7 years ago.
So excuse me. So there
Sure.
was a moment with that example with like a line. Yeah, there is the first example you showed,
Okay.
right? And the generated data, like the generator in that particular run produced data only which covered only part of the true like underlying distribution, right? And
Yep.
is it always the case, or it was just due to some random kind of was it random, or in this particular example it usually converges to this
Oh,
only kind of, as I say, I think that might be kind of closely related to mode collapse, right?
yeah. There's actually discussion. Maybe that's the answer. I'm not expert on this, right? So there is there's a discussion later on where about coverage, right? If you use KL divergence, what happens is that you have to cover every sample that's in your data set. You cannot not cover it. But with GANs, the this formulation of the GAN turns out that it doesn't have to cover it. Maybe I can just go there because I don't think it's related to anything. Let's see, where is it? Where it is? Yeah, here. So suppose this is our data. Then KL divergence will try and cover everything. It has to, and so Jensen JSD is our Jensen-Shannon divergence. It can just go to one mode, and so here's the example. So if you use maximum likelihood, if it's multimodal, then it has to cover all the modes. But
but in that example, I think the reason like here it's kind of more clear because we have like two modes, right? And but here we don't have like a mode really, but still the coverage is not full, right?
yep, I see what you mean. But so maybe this this idea here is so okay. This is the forward and the reverse KL divergence. So you have to bear with me for a minute because it takes a little bit to so this is a definition of the KL divergence, right? So dKL of P of x and Q of x is the expectation of the log of P of x by Qx. I wrote it as integral. And then the left-hand side and the right-hand side are not, they're not equal if you flip them around, right? P of x and Q of x. And so if you use this part, the left hand, the forward part, what happens here is you have P of x over Q of x. So if P of x is greater than 0 and Q of x is 0, so this is our real distribution has some value, but our other distribution does not have any value, then this is infinity, right? Here for this small portion. So there's like a very, very strong incentive if you're using KL divergence to cover every single point. But the one that we use is more similar to the reverse one, where the Q can P can be greater than 0, but Q can be 0, and there isn't as much penalty because you flip it over, and then P is greater than 0, but Q is 0, so there isn't any penalty. There is minimal penalty, right? So this
Right, makes sense, and so we can relate this to the actual loss function used in our example, and it would be kind of like a reverse scale divergence in a sense that we are calculating KL divergence with respect to the kind of this generated distribution of the P, right?
Yeah, so I think that's like the high level way of thinking is maybe that's the way it is, because they do say this is more similar to a reverse KL, the Jensen-Shannon divergence. Yeah, Jensen-Shannon divergence is more similar to the reverse than to the forward, where you don't have to cover everything, and as you said, leads to mode collapse. But perhaps that's why, yeah, it failed here. But it's not covering it this time. But yeah, in that way, that maybe explains it.
Okay, so the like underlying reason in like to summarize is that we don't have like much penalty for the data points which are in our like data distribution but not produced by generator, and the main penalty comes from or like loss comes from the generated samples which are not in data. But if we have some data that is not generated, we don't have penalty in this formulation, right? And can we? Oh, okay. So we have here this Jensen-Shannon and KL divergence. Okay, cool. Yeah, thanks.
Okay, yeah, we will. It's go over it in there's a whole derivation of why this is the Jensen-Shannon, why the Gan equation turns into that in a little bit. But I'm just skipping ahead a little bit here. But maybe that explains it. But okay, so I can continue on. So these are the Gan samples from 2014. I guess now it doesn't look that great. Yep. So the next problem that we need to think about is how do we know our GAN is doing well? Before we could use nits or bits per some. What was it? Nits. We could use something on the likelihood. Some sort of like the compression metric. I forgot what the name was, but we could use that to see how good the model was, how well it was representing the model. Bits per dim, sorry, or bits per dim or nits per dim. But we can't, right? Because we don't have that likelihood model. Okay, so how do we value? So there's a few suggestions. So this is the first one, the parson window density estimator. It's a very fancy name for something that's probably a pretty simple idea. So so this blue slides are the ones that I made, or parts of the slides that are colored blue is the one I added to it. I made a copy of the original slides and I added some of my own. So the parson window density estimator is the same as the kernel density estimator. As this, they're the same thing. They're just different names. So what it tries to do is we want to estimate a continuous density function just from the data. And how do we do it? We just grab a whole bunch of continuous distributions. Okay, so if we just think about when you think about continuous distributions, okay, and these abstract, we can just think of it as normals. So we grab n normal distributions, each centered at x high and with bandwidth h. So bandwidth is just a scaling factor. So you can see it scales the data by h, and then it does 1 over h. And then, so if you think about normal, it's acting as a standard deviation and also as a scaling factor in the front. But then you add up all of these different k's, that's for each of your data samples, that's centered at each of your data samples. And then you create a continuous distribution. And so that's called a kernel density estimator. So you just have data, and then for each data you just put a normal around it, and then you sum it all up. So, or it could be any. They say it could be any kernel, but each of them has their own scaling factor, right? And or the data has its own scaling factor. So that's the general idea of it. You're just making a histogram, but instead of like blocks of histogram, you put normals on top of it. Okay, and so, but this has also some problems, because then you have to figure out the bandwidth, because if you have too small a bandwidth, then you have all these like fluctuations, right? Because each data point has a normal in it, and you have these enormous like very focused normals. So this is the reference data, and then 0.3 is probably the best one to use. So then you have two trouble. You have another problem is that once you have the data, you also have to figure out h, and then you have to get the metric from a given h. Okay, and so this was used for some papers in 2014. I mean, this seems like the first thing you'd do if you wanted to, because you don't have the density function, so you just try to approximate it from the data. But this has problems for higher dimensions. So this is the actual log likelihood, and this is the estimate, and never gets there. It's in a completely different. It is in a completely different place. Yeah, and so there's a table of these things. So yes, and he says somehow you can cheat the distributions to do better than the actual distribution. So okay, probably need to go into the paper to figure out what's going on here, but I didn't do that. Okay, so we can just go to the next one. The next idea. This is kind of yeah, this idea is pretty out there. So instead of going into this high dimensional space, because we have all sorts of problems in high dimensional space, can we just do something else? And so the idea is like a good generator should generate samples that are semantically diverse. So it shouldn't just produce the same thing over and over again, or just one type. It should produce a very diverse thing, a set of things. And so the inception comes from the CNN inception, right? The famous inception classifier network. And so what they're doing is that in inception, let's call py of x, meaning y is if you give it an image x, it will give you a vector y of 1,000, a vector of a length 1,000, right? And that tells you probability of what it thinks of each image in its class is. And so so what we want to do is, if we generate an image, then we want, inception to say, well, I see this object. And so it should have low entropy. Low entropy means that there's one out of the 1,000 vector, one is very high, the others are very low. So we want it to have low entropy. So if it's not sure, it just says it's 1 over 1,000. It's almost the same in all of these numbers. Then it has very high entropy. But what we want to have is image inception to say, you generated a dog or you generated a cat, and I don't know what else is inception. Like you generated a plane, and instead of like I don't know, it looks like a dog plane, and all these things. So okay, and also the other thing is there should be as many classes generated as possible. So we shouldn't just generate dogs, but it should generate everything: dogs, cats, planes, everything. And so if we look at the distribution of all of the labels generated, it should have high entropy so that all of the classes are covered equally. All of the 1,000 classes are covered equally. So using this idea, then they came up of the inception score. Okay, so this is just, I made another slide so we can just transition here. And before we go back, because it's just a whole bunch of formulas there. So let X be our generated image from the generator. And so Py of X is the probability of labels using inception. So as we said before, we want low entropy so that it's sure that we generated something. We generated one thing. And also P of Y, and we so this is us saying let's go over all of the latent space, and we generate everything that's in the latent space, and then we get the classification label for everything that's from the latent space, and then we sum it all up, and this is it's our vector. Then we want high entropy here, so all the labels are covered, right? So this is just saying it's a fancy way of saying generate generate a huge number of images from the latent space. And just a refresher in case forgot, the equation of the entropy is negative expectation of X belonging to this probability P of log of P of X. And KL divergence is given by expectation of the log P over Q, right? So just a refresher, because it's used in the previous slide. So I'll go back to that slide. So here in this inception model, so we have this P of Y given X. X is our image that we generated, and this will give us the labels for that particular image. And then the marginal label distribution is all the labels from all of the images that we generated. Right? So this is written slightly different than mine. This was from the paper, and this one is how Peter wrote it, but it's the same thing. Instead of going over Z, it's going over all the X's, the generated X. Okay, so this is the inception score. So it's the exponent of the KL divergence of the label with the marginal label distribution. So the idea is that, and we want the score to be as high as possible. So the idea here is that when we look at one image and we look at what all of the images, we want it to be as different as possible. If they were the same, then means that whatever we took from the latent space just generated very similar images. So if this is a dog, and if the marginal is also a dog, then obviously it's not doing well because all it's making is dogs. So what we want is this marginal to create all of the different labels: dogs, cats, planes, and then this one to say, well, you produced a dog here and you produced an airplane here. This would also fail if it said, I don't know what it is. It could be anything. And then the marginal also says, well, you produced, everything. So that would also have a low KL divergence. And just from the definition, so this is just using the definition from the other page. The log is, if you have log a over b, then it becomes log a minus log b, right? So that's a slightly different form. But then this, the p y of x goes over here in the expectation. And this is the same as expectation of a log is the same as the entropy. So it's basically subtracting the entropy of we want this to be high. We want we want this to be low. We want this to be high. So this inception score matches up what we want to do. So it's pretty far out there because you're using a completely different neural network to try and score your GAN by using classification. And so real data has pretty good scores, and then our methods probably means the paper that used it. It has, the more realistic it looks, then it has higher methods. And if it's just others and fuzzy and it's not quite sure what it's generating, then it will have a lower inception score. Okay, and so this another one here that's also probably just comes off from inception is that inception doesn't, the other previous score has some problems. If you just create one from each class, it can do really well. So the idea here is not to just look at the label at the end, but to look at some of the feature spaces of inception before it gets to the label. So you measure okay. So you embed X into some feature space of inception. That's before it does the classification, and compare the mean and covariance of the random features. So instead of just saying what class does it produce, you actually go and look at the earlier activations or earlier feature space in the inception. So that's the Fichet inception distance. And yep. And so if you make something noisy, so it has advantages that the inception score stays about the same, even though the image quality is degrading. It's getting blurrier. It can still recognize it, I guess, and but then the score increases, meaning that it's worse. And there's more of these. If you add noise, disturbance. Okay, this is probably a summary. Oh, sorry, it's probably a summary of generative adversarial networks. So it's the key pieces again. So we want fast sampling, no inference. So yeah, we only notion of optimizing directly for what we care about, perceptual samples. So any questions before we get to the some of the theory on GANs? So the last yeah, the last section was just about how do you measure how good the GAN output is, some metrics. Okay. So this, so the Bayes optimal discriminator. So the discriminator is the one that, what is the best discriminator? We want to be able to able to figure out how to get the optimal discriminator, given our the current true distribution and the generated distribution. Okay, so this is a big equation, so we can go through it step by step. So V is our, this is the same as the loss function we talked about. So we have the expectation with the loss, expectation with respect to the real data, the log of the discriminator. We want this, this is the discriminator to classify the real images, and this part is the generated images, right? The expectation of the Z from the latent space. We want 1 minus the, so that it can classify it as fake. So this is the real part, this is the fake part, right? So this is the loss function that we looked at before. Okay, so the next step is converting the expectation into integrals. So you add the, you multiply whatever is inside by the probability, right? So this is probability of X coming from the real data, and then probability of Z coming from the latent space. So all they've done is just change the expectation into an integral. Okay, and so in the next step, so instead of Z, it's just changing the variable into X, because if you pass Z through G, then you'll get X, which is an image. So we can think of it as probability of generating this image X, and then the discriminator labeling it as true or fake. Okay, and this line is a little bit iffy to me because this X and this X are not the same, but I don't know what conditions you have to satisfy, but it's just combined it into one integral, right? Okay, so because if you have two additions on the integral, you can move it into one, I guess, provided that we're going over the same axis, but I don't think we are, but there's probably some assumption that makes this possible. So all it is just removing this plus and moving this plus inside the integral and putting both of these under the same integral, right? Okay, so what is the point of this is that now we, okay, let me go back. We want to find the optimal discriminator. So we want to find the optimal D. Optimal discriminator. So what we do is we take the gradient of this. We take gradient of this and set it to 0 to find the optimal one. And the gradient is of course respect to D of X. And since the integral is based on X and not D of X, and they might be connected, but anyway, here they assume it's not. So the equation just becomes the same as this one. So gradient with respect to Y. So Y is the D of X. So A log of Y plus B log of 1 minus Y equals 0, right? So this is what's going on here. So trying to optimize. And yeah, again, this is d of x and x are not related here. So there's another assumption here. And so if you calculate this, the gradient is just the derivative, right? And then the log of the derivative is 1 of y. So this becomes a 1 of y plus b 1 minus y equals 0. And if we solve for y, the answer is a divided by a plus b, right? Which, if you substitute everything back on what ab means, the optimal discriminator is p data of x divided by p data of x plus b of g over x. So for each x, there is a sort of like a discrimination point that it can say, I know this is x, this is real, and this is fake. So this is the intuition. So this is our real data distribution, and this is our model distribution, and this would be the optimal discriminator. So we can say, well, if it's which side of it is, then we would say if it's real or fake. Okay, so what interestingly happens is if we move the optimal discriminator back into the original loss function, so it becomes log of p data blah blah, and then expectation of log of 1 minus of this, and then if you calculate it, it becomes because you're taking 1 minus this fraction, it becomes pg of x, p data pg of x. And if you look at it, this is the KL divergence, right? This probability matches this probability matches this, so you can write them as KL divergence. And so this turns out to be the Jensen-Shannon divergence. So I have a slide here. Okay. In the lecture, they assume that you know what Jensen-Shannon divergence is. So this is a quick slide on that. So Jensen-Shannon divergence is symmetric. It's finite, and so you can take the square root of it, and it can be used as a metric. I think with KL divergence, it's not symmetric, it's not finite, right? So it's a way to fix KL divergence if you want to use it as a metric. And so the metric has to have all these properties, right? So it has to be symmetric, it has to obey all these different rules. So the way this formulated is, so you have two distributions P and Q. So you let M equals half of P and Q. And then so JST of P and Q is half of the, so this is D is the KL divergence. I should have written KL down here, but the Wikipedia article didn't have the KL here. But it's DKL of P with M. M is the one that's half this, and Q with M. So that's how this is defined. And as we can see, this is so we ended up with KL divergence of data with half of this, KL divergence of Z and half of this. So this is actually the Jensen-Shannon divergence. And so the whole idea is that this this loss function that we use, you know, for GANs is actually the Jensen-Shannon divergence that we're actually optimizing for that metric. I mean, there's a bunch of assumptions in the middle, but that's the idea. So instead of KL divergence, we have this version of the KL divergence, kind of smoothed out version of the KL divergence. And yeah, we looked at this slide, but I'll go over it. So this is our data. And with KL divergence, it has to cover everything. And this probably is in the next lecture. And Jensen-Shannon can just cover the most important bit of data. And it's not worth it to like try and cover that part. Right. So here's maximum likelihood. It will try and cover everything. Even though there's nothing here, it has to put something in there. But reverse KL will cover one mode. It will say it's better to cover here than to spread over everything. And I already went through this, so I can go through this again. The idea is that if we use KL divergence, then the equation becomes P of x by Q of x. So if P is greater than 0 and Q is 0, then this becomes infinite. Right? So if P is 0, Q is 0, then equal infinite. And so KL must cover everything. But if we use reverse KL, then Q and P and Q are flipped. So Q can be 0 up here, even though P is 0. So it only adds a little bit to the KL divergence, or it doesn't add anything to the KL divergence. And JST is not exactly reverse KL, even though this slide shows it to be exactly the same. So something happened here. So something happened here in the, because in the lecture they have different images. So I'll go back to this one. So yeah, so this is the reverse one. The P and Q are switched over in the KL divergence. But in the Jensen-Shannon, it's close to reverse, but not quite. So it does put a little bit of weight into the one, but it doesn't have to fully cover it.
So the slides are different, like this version on the site and the one demonstrated during the lecture, right?
Yeah, they're different. So I don't know what happened.
Which one is correct? Might it be that the slides were corrected after the lecture was done and actually the Jensen-Shannon divergence results in the same solution for this case, or is it just a mistake in this slide?
I don't know. Yeah, I don't know. I didn't look into it. So
okay, just probably worth checking that, I guess.
yeah, they probably can probably just do it in PiTorch, right, and see what happens.
Yeah, maybe it will be related to the homework somehow. And,
yeah,
be checked.
Yeah. Okay. Good. Okay, so this is called mode covering versus mode seeking. Yeah, for compression, we want to ensure that we want all the modes to be covered, because we don't want, we haven't gotten to compression yet, so it probably doesn't make much sense to talk about this. But for our case, if we want to generate good samples, it makes sense to go do mode seeking, because then we generate really good samples from one single mode, then rather than create a blurry one across multiple modes. But and he does that with a caveat. Says, well, it's probably because you're if you used a mixture of Gaussians, all this problem happens because you're using a single Gaussian to fit a mixture of Gaussians. If you already used a mixture of Gaussians, this wouldn't be a problem. So instead of just having one peak, if you're allowed to have two peaks, then maybe this wouldn't be a problem. Okay. So this brings us to mode collapse, which we'll also get into a little bit more down the line, and how to fix it. But this is just one of the the famous famous problems with GANs. It's mode collapse. And let me check. Okay. Excuse me. So what happens in mode collapse is that the generators, so this is our target with different modes. The generator figures out that, that there is one point that produces something that can fool the discriminator. So all of the gradients go towards that point. So no matter what you ask it to generate, it will just keep generating from this single point. And so what then happens is the discriminator learns that the fakes are all coming from this point. And then what the generator does is, instead of trying to model all the different modes, it looks for the next mode. It just switches over to another mode. And then it takes a little bit of time for the discriminator to catch up, saying, well, you're just generating from one point, because at first it looks like it's doing a good job. But then as soon as it catches up, then the discriminator flips over to another point. So you can see it goes over here, then goes over here, then goes over here, and goes over here. So instead of generating from all the points, it just like focuses on one point here. And then when the discriminator catches up, it's like, oh, I know what you're doing. Then it just switches over here. And then when it catches over, it'll like flip over to something. So that's a mode collapse that's present in these GANs. That can happen from our formulation. And it also comes from our loss function, right? So, okay. And I forgot what this. Okay, yeah, and so we want to talk about other problems, another problem with GAN. So this is our discriminator, and see the oh, sorry, there's a chat question. Oh, okay, Mike, I'm not sure what the.
You have the figure on the second page.
Okay, second page. Oh, this is the discriminator.
Yes. Yes.
Okay, great.
As you can see here. This is between the JS and the this is P of X, this is Q of X, and this red line is the D of KL, P, M, and This is from M line. They have taken a third line in which they have tried to give a distribution of with respect to this line. So if you can see from here, uh, this one and this one. So these two are the differences between the day of JSP Q and day of KLPQ, day of KLQP. Yes, these are the original figures. So, yep. This is the right way of representing.
Okay. 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 Let me go back to the back to Gan's. Sorry. Yeah. Okay. So yeah, this is just the discriminator part, right? So in the first step, only the discriminator is updated. So Peter asked the question: is it feasible to run the inner optimization only the case steps in the algorithm? Is it possible to just keep running this and running this until the discriminator is really, really good? Or it's very sure, sorry, it's very sure. And then say, well, let's run the outer one after that. And turns out there's a problem called discriminator saturation. So once the discriminator is sure, it doesn't, it has no gradient and it won't change its mind. It just won't update itself. And so this comes from some, from the fact that the discriminator is the sigmoid, the last step on the discriminator is a sigmoid. Right, so if you look at the sigmoid and we look at the sigma of log 1 minus the sigmoid, and we take the derivative of it, here the gradient is 0. So once it's confident, there's no gradient left. And so it will not update itself. So no matter what happens, it's sure it knows what's going on. So a simple way is just to do alternating optimization, right? So you do the discriminator with the full equation, and then you do the generator with the smaller, just the one that's relevant to it. You update it, and you update both of the gradients one at a time. But yeah, balancing these updates are hard. Because they're both fighting against each other. So these gradients, one update might be not good for, so so the is to change the game, or change the game. So instead of so the first part is the same, the first part is the same, but in the second part, when you want to train the generator, we maximize, instead of minimizing the log of 1 minus, we maximize the log of It's the same formulation. It's a similar formulation, but they say it's not a 0-sum game anymore, because, both are playing a slightly different game, I guess. So I'm not sure why that's not a zero sum anymore, but the idea here is that if the generator gets super confident, so this is sigma fx, and this is the negative log of sigma fx, the derivative here, it doesn't have it's around here at this point that it still has some gradient. But once it's very sure, oh, sorry, it still has some gradients down here, but then only when it's very sure that okay, I'm not. I don't know what this x is. I forgot to look that up. But yeah, but on the general sense, what's going on here is that as soon as it gets confident, so I don't know what this x scale is, but with this, the gradient is 0. But in this case, this figure is here. In this case, the gradient itself is not 0, and it's only when it's uncertain at this region, it's the gradient is 0. So the problem is flipped around so that during training there is more stability.
If first case we are not getting any gradient in the case when the discriminator is confident that the generated image is fake, right? So the first case when we play the zero-sum game and the generator objective includes this log 1 minus discriminator of generator. So this, yeah, the central, right? And the second case, the generator objective is to maximize the probability of being classified as true, right? Instead of minimizing the probability of predicting that the image is fake, we maximize the probability that the image is true, right? So it's kind of similar, but not exactly. And yeah, so this third, right? And in this case, we are getting a gradient when the generated image is predicted fake, right? So the leftward part of the plot, and but we don't get any gradient when the discriminator is confident the generated image is true. So I mean it's from the data distribution. So in this case, in the rightward part, the discriminator fails to kind of classifies a fake image, right? And we don't get any gradient. And it's, I believe it's less of a problem because, yeah, when our kind of generated image is close to the correct image, yeah, it's not so bad, right? As that we don't have any gradients for generator. Is that correct?
Yep. That's yep. That's perfect. Yeah. That's the yep right explanation. Yeah. And it's all, yeah, it seems all based on the sigmoid and how these, how they react. So, because the last step is the sigmoid, right? So if the x value that comes in is negative, it goes towards 0. If it's positive, it goes towards 1. So so here, if it's highly negative, the gradient is 0. If it's highly negative, the gradient is not 0. Only when it's sure. Okay, so can go to the half hour. We can go to DC Gan. Is there any questions or anything we need to discuss? Any questions? Okay, so I'll go forward. So we go into called DC Gan. So this section, so we went to these 4 sections before. So the last one was some theory about the different metrics and how they related to it. And before we had the evaluation and some introduction on GANs. So this one is just about progression, how it has improved throughout the years. And so we can just start with this paper called DC Gan, Deep Convolutional GANs. So this has a I've found that this tutorial, it's on the PiTorch tutorial, has a really nice DC Gan tutorial. So I'll refer to some of the points here. Okay, and so one of the things they did was something called a deconvolution layer. So we can think of the generator as taking the inverse. It's a decoder, right? So you take the latent and then you create the image out of it. So so you're doing the reverse of what a classifier would do. So they added a deconvolution layer. So deconvolution layer is just a transpose of a convolution layer. It's a variation of it. So in this case, when you're generating, let's see, this is the same image here. So when you're generating, you use con transforce 2D. And whereas when you're discriminator, you just use con 2D because this is just like a classifier, right? Image classifier, but you want to use a transpose version of it. Okay. And so there's a list of improved changes. So they removed max pooling and mean pooling. So apparently they had it in the original GAN. It didn't work very well with GANs. So upsample using transpose convolution. So we already talked about this. So instead of using regular convolution, they use transpose convolutions. Downsample with strided convolution and average pooling. So strided convolution means that you set the stride on the convolution layer to more than 1. So it doesn't go from one pixel to another. It jumps over pixels. So in this case, one of them. So this is one of the bad things. They didn't specify what parameter was what. So it's one of them is probably a stride parameter. You can see which one is the stride parameter. Or if, yeah, I don't know if, yeah, this is the stride parameter. It's stride. In channels, out channels, kernel size, stride. So yeah, in channels, out channels, kernel size, and stride. Probably this one is the stride. So the stride is more than one. Okay, and average pooling. I don't know if they actually use average pooling. I didn't see it.
It's a bit confusing for me. So they on the slide they say remove max pooling and min pooling and use average pooling. And if I'm not crazy, mean and average means the same thing, right?
Yep.
So that's kind of doesn't make much sense. And strided convolutions and any kind of pooling act kind of similar way. So you can downsample using pooling, or you can do strided convolutions and you will downsample as well. So probably that's just a mistake here. So
Okay.
the average pooling, I don't know, either means something that is not usually understood by this word, or I don't know, or it's a kind of a typo.
Okay. Yeah. Unless like mean and average means something else, they could be. Okay. And then, so the other thing is they use leaky ReLU for the discriminator and ReLU for the generator. So here we go. So this is ReLU for the generator, and the discriminator has the leaky ReLU. So what is leaky ReLU? So ReLU has X, and otherwise it's 0, right? Otherwise this part is 0 in ReLU. But in leaky ReLU, it's some negative slope times the X. So here's a picture of it. I mean, you could barely see it. It's a little bit curved, right? So that it's slightly leaky. I guess that's where the leak is. If it was ReLU, then it would just touch 0 here, but it's slightly below. Okay. And output for nonlinearity, tan H for the generator and sigmoid for the discriminator. And so let's go back here, and there's a sigmoid at the end of the discriminator, and for the generator, there's a tan H at the end. Okay, and batch normalization is used to prevent mode collapse. And batch normalization is not applied to the output of G and input of D. So this one is, yeah, so they say not applied to the output of G and input of D. So output of G does not have a batch norm, and input of D does not have a batch norm. So there's like one step missing. So yeah, these are very technical things. I'm not sure what exactly effect it has. But yeah, and then and these are the parameters for the optimizer. They use Atom. So the other confusing thing is they call batch norm as also this thing. So when training the discriminator, what they want to do is they want to train it using the real images and training it using the generated images separately instead of mixing them together. I think they also call this batch norm. So that's a little bit confusing. So here in the training part down here. So we train with the all real batch here. So there's a backward, and this only the discriminator is being trained. And then there's the fake batch, and where you train the discriminator again, the D part, right? So and then you train the generator part with the fake fake images again.
So we avoid computing batch norm on the combined batch containing real and generated images, right?
Yeah,
So that's
I
the
think
reason
that's
for that. And in more modern networks, they usually use instance norm, and that is not necessary anymore, right?
okay. I don't know about it.
Oh,
I
I think we will get to that at some point, probably.
oh, okay. Yeah, there's this batch norm here also. It's being applied here in batch norm, which means you normalize this layer, right, between before you send it out, um, and you have a parameter or something, the number of parameters here. Um, that's also trainable. So
Yeah, so the batch norm computes a statistics, the mean and standard deviation on the batch. And in this case, we don't want to mix the fake and real data to avoid this kind of computing this statistics to get together, right? I
yep,
believe that's what it means.
okay,
And like to rephrase it, I guess we need to feed the real and fake images separately because we have a batch norm in the network. So,
okay. I see. I see. That makes a lot of sense. Okay. So that's the whole batch norm problem. Okay, great. And so some results here. The bedroom data sets produce some good ones. I barely can see anything, um, but from far away it looks okay. It looks pretty fuzzy. So um, so some faces it generates. And so yeah, and so this one is actually surprisingly fun. I actually put this on PiTorch and ran through it. And this is supposed to be a GIF, but it doesn't play. But if you run this, put it in code, and this is actually an animation. So you can see the actual data being generated step by step.
cool. So you can train the face generator from scratch for like how long does it take?
For me, it trains for a while, but you can at each training one, it will generate this picture. So at some point you can just stop it because it gets better, but it gets better much slower, right? I think on my computer with the GPU, it just took about a few 5-6 minutes before it produced something of good quality.
Oh, cool.
Yeah, it is very fast, but the pictures are tiny, very small. So it didn't take very long. And I think all the parameters are optimized by the tutorial writer. But it won't produce big images that are very good, but it will produce these tiny little images that, that look okay.
So what is the resolution there, the user?
Oh, let's see. Okay, I should just look at the input. They specify here. Nope. Okay, NZ and NZF. Where did they load the data? Sorry, I'm scrolling pretty fast. I will put this in the chat.
Oh, cool.
And
Yeah, sure.
you can. Sorry, that would be. It's here. It's somewhere here, but it's in the loader, right? So loader, data loader somewhere. But it, normalize image size. Okay, B size to image size. Okay, let's see. 64 by 64, or yeah, 64 by 64, I guess.
Oh, so it's not like that small, but not something that you can kind of use, right? But yeah, still it's nice. But probably it's easier to generate like fine looking results on something that is small, and then you plot it even smaller, and it looks kind of a bit better. But if you kind of enlarge the image, you will see the artifacts of the generation.
Yep. And yeah, this tutorial is tuned so pretty well, so that's why. Yeah, it's pretty fun tutorial, and it's very well written, and everything is clear. Okay, so that was that, and then they can also do smooth interpolation in high dimensions. So I think the perspective changes in the bedroom. So as you move one of the latent variables, the perspective that you're looking at the bedroom changes. It's generated from ImageNet samples. Okay, and the other one I think that was famous was the vector arithmetic. So you take the smiling woman, take the Latin vector, subtract it by the neutral woman labeled vectors, and add neutral man to it, and then you get smiling man. So you can do these vector arithmetic to produce. I think this also works in the anything that has latent space.
Yeah, this is pretty cool. So this is like completely emergent property. I mean, we don't have anything that encourages this kind of relations, right? But it just emerges naturally when you train the network. It's really cool.
And then the famous sunglasses, I think you take man with sunglasses, subtract man without glasses, plus add women with glasses, then you get women with glasses. And for if you just do it by image, arithmetic instead of the latent space, you can see the clear difference of what's going on. And this is the perspective change. So looking from the left side to the right side of the face. And yeah, so this is a side note of representation learning. So they said they added a classification node to the end of the DC GAN, and then I think just retrain the last classification node while holding the weights frozen. And it performed pretty well with the models that had there. It's not as good as the best, but it's competitive. So it actually learned some representation of the ImageNet data set, or whichever this was. I don't know if it was ImageNet, but it learned the representation without having to explicitly use supervised learning. So you could train it on a large set of data, and then at the end just improve it with some label data. So it already had some representation learned from there. Okay. And so the problems they had to address was unstable training and lots of hyperparameters and brittle architecture.
Oh, Morten, I had a question. Does he
Sure.
cover anything about, what the scores are from the evaluation metrics, like the inception score or vision, whatever the thing to evaluate it?
No, I don't see it. Can look up the paper. I'm sure they have
that
it.
would be interesting to see how it does with respect to those metrics. Right?
I think this is the one, and okay, so probably in the results section, details. This is the details.
So the paper is by Alec Redford, who is author of GPT models, right?
Oh,
Anyway, if it's not, we'll look at it offline.
okay. Yeah, I think that's what that was also saying, that his goal was not to actually compare them, and he was more interested in classification and representation learning. Because that's what the metric seems to be like. This is the CIFAR 10 classification results, and classification only. It doesn't have those metrics.
It might be that Inception is, so the Inception network is kind of younger than this one.
Oh,
Maybe.
okay.
So
It's 20.
probably Inception score wasn't there at that moment or something like that.
Okay.
Yeah, I'm not sure about it, but just guessing.
Yeah, could be that paper with the Inception score. Oh, I don't know. Yeah, I don't know. Okay. Where was I? Okay, so we can go to this. Oh, we have 10 minutes, so we can either start this new, the next paper, which is called the Improved Training of GANs, or do you want to stop? Do you have any points we want to discuss?
No, I think people have to drop at 10, so in 8 minutes. So if it's likely to go beyond that, then we can stop here and then take it up at this point. Next
Okay.
session, if we think we can get through all of the rest of the second hour in the next meeting.
Okay, yeah, that sounds great. I think the lecture, he gets to the middle of this place here, the mini batch discrimination part. So we're almost at the same point. Yeah, okay, great. I think it's a good, like a point to stop, then going to the 5 improvements here.
I was thinking if it makes sense to swap the practical part for GANs with the second lecture on GANs, because like we have this 2 lectures dedicated to GANs, and it kind of makes more sense to do the practical part after we are done with lectures. If it will be okay with a person who signed up for the second lecture, and I believe we don't have yet anyone for the practice.
Yeah,
Yep,
we don't have anybody for the practice. Let me look. Let me see whether somebody has signed up, Arto, for the theory part of the second GAN related stuff.
It's Arshad. I don't know if he's here today.
No, he's not. Let me check with him, and that's a good suggestion. Maybe we can go through all of the kind of like the background of GANs and then get into the practicum. So let me check with him whether he'll be available 2 weeks from now to take that up, and then maybe we can finish up the theory. That's your suggestion, right, Arto, if I get it correctly?
Yeah. I just
Okay.
I'm just thinking
Yeah.
that
No, that makes
you
sense.
know, the lectures are kind of continuous stream. It's not like
Yeah,
we need
yeah.
the first lecture for the practice, or the second one is kind of something different. But it's just, and I think that in the course kind of schedule, the last homework was like out after the second Gan lecture was done. So I was.
Oh, okay. Sounds good. Let me check with Arshad whether he's available, and if so, we can do what you suggest.
Yeah, great.
Okay. Good suggestion. Thanks. Okay, thanks, Martin, for taking us
Okay.
through that, and we'll hopefully complete the remainder next week.
Okay. Well, yeah, that sounds great. Yeah, should be able to finish it up next week.
Okay. Thanks a lot, everybody. See you all next week.
Okay.
Yeah,
see
thanks,
you.
Martin, for taking us through it.
Yep, you're welcome. See you next week.